Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is 5.3, which is on solving trigonometric equations. Alright, so the instructions for every single one of them, or every single example, is going to be solved. Alright, so we're going to solve equations. So for example, let's say that we have sine of x minus radical 2 is equal to negative sine x. Alright, so what we want to do here is pretty much put all the trig functions on one side and everything else on the other. So doing that, I end up with 2 sine x is equal to radical 2, right? Add sine x to both sides, add radical 2 to both sides, giving me that sine of x is equal to radical 2 over 2. Now, at this point, what is this question saying? This question is saying, what is the angle for which sine of that angle is equal to radical 2 over 2? And it turns out from the unit circle that there are two solutions to that. All right, it happens first at pi over 4, and then again at 3 pi over 4. All right, so those are the solutions within the unit circle. However, we have to consider that sine as a function does not only exist in the unit circle. In fact, as a function, it looks like this, right? Repeating forever and ever. And this question, where we have sine of x equals radical 2 over 2, can be interpreted to mean where is the sine function at the height of radical 2 over 2. And as you can see on this poorly drawn graph, this happens multiple times. Right now, what we've got are these first two solutions, all right? But we're still missing a whole bunch of them. Well, to account for that, what we need to do is add the period of the function to our solutions, all right? Because this next point over here would be just adding the period. Similarly, from here to here, these right here would also be just adding the period. All right. So, and that happens multiple times forever and ever in both directions. So what we need to do is just add multiples of the period to get to all the others. So what we're going to say here is we're going to say, well, for this solution, for x is equal to pi over 4, well, there's going to be pi over 4 plus 2 pi n, because we're adding the period of sine. And over here for 3 pi over 4, we're again going to say plus 2 pi n, because we're again adding the period of sine. All right, so we need to account for that in our solutions here. All right, let's do another one. Example B. Let's say that I said, or that we have 4 sine square of x, and let's do cosine. 4 cosine square of x minus 3 is equal to 0. All right, well, solving for cosine here, I end up with cosine square of x is equal to 3/4, right? Add 3 divided by 4. Telling me now that if I take the square root of both sides, I end up with cosine of x is equal to plus or minus radical 3 over 2. All right, radical 3 over 2. I took the square root of both the top and the bottom there. And the plus or minus comes from the fact that we were taking the square root of both sides. Now, what is this question really asking? Well, we have this saying, what is the angle such that when I plug that angle into cosine, I get radical 3 over 2, or I get negative radical 3 over 2. And for each of these, based on the unit circle, we end up with two solutions, all right? For this first one over here, for radical 3 over 2, for cosine, well, that happens at pi over 6. And it also happens at 11 pi over 6. All right. For this next one over here, for negative radical 3 over 2, that would happen then at 5 pi over 6, and then again at 7 pi over 6. All right. So now that we've got that, we need to also account for the fact that just like sine, cosine is a wave, right? So because of that, well, we can interpret this first question over here, well, not that one, this one over here, to say when is cosine equal to this height, and it was supposed to hit those two as well. Maybe there we go. When is cosine equal to that height? That's that first question. But then this one over here would be when is cosine equal to this height. All right. And well, just like we saw with sine, the period is going to make sure that we hit a whole bunch of other ones that we haven't accounted for, because these are just the solutions within the unit circle. So what we need to say here is, well, we need to add the period of cosine to every single one of these. All right. And those are our solutions. Now, in a problem like this, I do want to show you that while this is a fine enough final answer, this first row right here, perhaps I'll write it this way. These two solutions can be rewritten or combined to say x is equal to, sorry, not those two, these two. There we go. X is equal to pi over 6 plus n pi. Because to go from pi over 6 to 7 pi over 6, all I need to do there is add pi, right? So this period is going to essentially be shortened to be just n pi. Similarly, with the other two solutions there, this one and that one, we can shorten that and say that x is just equal to 5 pi over 6 plus n pi for the same exact reason. When I add pi to 5 pi over 6, I end up with 11 pi over 6. But like I stated, these first two rows are good enough as your final answer. All right, and that looks like that's a square. Let's fix that. There we go. Way better. Next one. So that was B. C. Let's say that I had something like cotangent of x times cosine square of x is equal to 2 cotangent of x. All right. So first, I'm going to show you the incorrect thing to do here. All right, because it becomes very easy to mess these up. So this next thing is wrong. So we've got cotangent of x times cosine square of x is equal to 2 cotangent of x. So I see here that we have cotangent on both sides. So I'm going to divide by cotangent. And I end up with simply cosine square of x is equal to 2. Now, in here, this would tell us that cosine of x would be equal to plus or minus radical 2. But radical 2, let's look at that. Radical 2, well, that's bigger than radical 1. And radical 1 is just 1. Right? Now, why do I care about this? Well, the maximum value of cosine is 1. The minimum value of cosine is -1. So radical 2 is outside of that. So in other words, here's 1. Well, here's -1. Here's 1. Over here is radical 2, and over here is negative radical 2. So it is outside of the bounds of cosine. So what's my point there? Is that this gives us no solution because it's beyond the range of it. All right. Now, this is overall technically incorrect. All right. And not that everything was incorrect, but there's one very crucial step here that is very, very wrong. And that happened at the very beginning. Crossing these out and dividing both sides by cotangent. All right. The rest after that is going to overlap with the correct version. So let me show you what I mean. So this is the correct version. So what we have here, it was cotangent of x times cosine square of x is equal to 2 cotangent of x. The correct thing to do here is put everything on the same exact side. So I end up with cotangent of x times cosine square of x minus 2 cotangent of x is equal to 0. At that point, I'm going to factor out a cotangent. So if I factor out a cotangent, I'm left with cosine square of x minus 2 is equal to 0. And here I've got the product of two things equaling 0, so either the first one is equal to 0 or the second one is equal to 0. Now the second one over here, we already know what happens with this. There was nothing incorrect about how we did that, and we got no solution, right? There was nothing incorrect about that process later on. But what we missed in the other one, in the other version, is this piece right here, cotangent of x. We canceled it out. Essentially what we did, because this is equal to 0, what we did before was divide by 0. But now that we have the cotangent of x is equal to 0, well, this is asking where on the unit circle is cotangent equal to 0. Now another way to think about this is that cotangent is cosine over sine. And I've got a fraction there equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0. And now this is a much easier thing to think about on the unit circle. All right, so where's cosine of x equal to 0? Well, it happens at pi over 2 as well as 3 pi over 2. All right, now what we need to do is add the period to this. But we need to add the period of cotangent because we were working with cotangent originally. All right, so now the period of cotangent is just pi. So we're going to say this is pi over 2 plus n pi, and this plus n pi. However, notice here that technically that second solution doesn't add anything of value, because to go from pi over 2 to 3 pi over 2, I could just let n equal 1. So in other words, I just add pi, and I'm there already. So a better solution here would be just to say that x is equal to pi over 2 plus n pi. But if you leave that there, not too many worries. So perhaps I'll do it this way. Redundant. All right. Next one. So again, what happened incorrect over here was that we divided by cotangent. Never, in general, never divide by a function or by a variable on both sides of an equation. All right, you end up missing solutions like these. All right, so that was example C. Right? Yeah, C. D. Example D. So let's say that I had 2 sine squared of x minus 3 sine of x plus 1 is equal to 0. But I'm going to add an extra thing here, and I'm going to say on 0 to 2 pi. All right, so I want the answer to be within the unit circle. All right, so all right, well, how do we do this? Well, the very first thing that we're going to do here is not work with this as written. We're going to do a u substitution, and we're going to say let u be equal to sine x. And then, well, what would this become? This becomes 2u squared minus 3u plus 1 is equal to 0. And perhaps I'll do all of this in blue. At that point, well, we know how to factor those, right? This is a quadratic, and we can use the AC method, multiplying 2 times 1. So we say, well, 2 times 1 is equal to 2. I need two numbers that multiply to 2 but add up to negative 3. That would be negative 2 and negative 1. So we have 2u squared minus 2u minus u plus 1 is equal to 0. From the first 2, take out a 2u. I'm left with u minus 1. From the second 2, take out a negative 1. I'm left with u minus 1. So we have 2u minus 1 times u minus 1 is equal to 0, giving us that u is equal to 1/2, or u is equal to 1. But the problem was not about u. It was about sine x. So what we need to say here is sine of x is equal to 1/2, or sine of x is equal to 1. At that point, well, we can look from the unit circle to get some answers here, because in the question itself said we needed to be within the unit circle. So where does sine equal to 1/2 within the unit circle? Well, it happens at pi over 6 and at 5 pi over 6. Where is sine x equal to 1? It happens exactly at one spot, pi over 2. All right? And again, this is from knowing the unit circle. All right, next one. So here again, because we had a quadratic form here, I opted to first do a u substitution. All right, so I highly recommend that you get into the habit of that for those kinds of problems. All right, E. Let's say that I had something like 3 secant square of x minus 2 tan square of x minus 4 is equal to 0. All right, now in here, the very first thing you'll probably note is that we're working with both secant and tangent. And the thing with these is you don't want to work with two different functions. All right, you want to work with just one function if ever possible. So what I'm going to do here is I'm going to replace one of these, and what I'm going to be working with is 1 plus tan square of x is equal to secant square of x. Right? That is the identity that I'm going to be using in order to solve this. So what do I mean by that? Well, we can use this in one of two ways. I already have what secant square is equal to there. So what I can do here is rewrite this equation as 3 times 1 plus tan square of x minus 2 tan square of x minus 4 is equal to 0. All right, so in there, I replace that secant squared with 1 plus tan squared. So at that point, we're going to say, well, if we distribute this 3, I end up with 3 plus 3 tan squared of x minus 2 tan squared of x minus 4 is equal to 0. So combining like terms here, I end up with 3 tan squared minus 2 tan squared is just tan squared, and 3 minus 4 is negative 1. So this is really just saying, where is tan of x, or tan squared of x, equal to 1? In other words, where is tan of x equal to plus or minus 1, right? Because I take the square root of both sides. Now, this technically yields two different equations, where is tan of x equal to 1, or where tan of x is equal to negative 1. And the thing about tangent is that we can rewrite it as sine over cosine. And this equation now, if I multiply both sides by cosine, would say sine of x is equal to cosine x. Similarly over here, I could say this is sine of x over cosine x equals to negative 1. So the question is really, where is sine of x equal the negative of cosine x? Let's rewrite that. The negative of cosine x. There we go. So in here, well, if we think about the unit circle, here you're saying, where is sine equal to cosine? Well, that happens at two spots. In the first quadrant, it happens at pi over 4. In the second quadrant, it doesn't happen, but in the third quadrant, it happens at 3 pi over 4. That's not true. It happens at 5 pi over 4. There we go. In this part over here, this is asking where is sine equal to the negative of cosine. Well, this happens in the second quadrant at 3 pi over 4. And then it happens again in the fourth quadrant at 7 pi over 4. All right, that's where they are negatives of each other. So those would be our 4 solutions. All right. And that was using secant squared to replace, using 1 plus tan squared to replace the secant squared. But there's 2 ways to do this problem. So let's look at the second way to do this. Oh, hold on. I'm just going to make sure I add here on the unit circle so that you know that we have found all of our answers. All right. So I'm going to copy this. And we're going to do the same problem. But we're going to call this E star. Now, rather than replace the secant squared like we did in the last problem, what we're going to do here is we're going to rewrite this equation as tan squared of x is equal to secant squared of x minus 1. And now we're going to replace tangent squared. So this version would look like, well, we have 3 secant squared of x minus 2 times, instead of tan squared, I'm writing secant squared minus 1. Then we have that minus 4 equaling 0. Now that we have this, well, distributing this negative 2, I end up with 3 secant squared of x minus 2 secant squared of x plus 2 minus 4 is equal to 0. Combining like terms, well, 3 minus 2 is just 1, so secant squared of x, and then 2 minus 4 is negative 2, that being equal to 0. And at that point, well, solving for secant, I end up with secant squared of x is equal to 2, so that secant of x is equal to plus or minus radical 2. Now, rather than think of this in terms of secant, well, actually, first, let's split this up into the 2 fractions, the 2 equations that this implies, secant being equal to radical 2, or secant being equal to negative radical 2. But if I rewrite this in terms of cosine, if we rewrite this in terms of cosine, we have 1 over cosine is equal to radical 2. And over here, 1 over cosine is equal to negative radical 2. Taking the reciprocal of both sides, well, on this side, I end up with just simply cosine of x is equal to 1 over radical 2. And this one, I end up with cosine of x is equal to negative 1 over radical 2. Now, 1 over radical 2 is just simply radical 2 over 2. So this will tell us that here we just have the negative of radical 2 over 2. And now the question here is, well, on the unit circle, where does this happen? Well, x is equal to radical 2 over 2 at 2 spots. At pi over 4, and also at 7 pi over 4. And x is equal to, cosine is equal to negative radical 2 over 2. At 2 spots, those being 3 pi over 4, and also 5 pi over 4. All right, so you'll notice there that we got the same exact solutions as before. Pretty much all the odd all the odd numerators of pi over 4. Right, 1, 3, 5, and 7. All right, so my point here is it doesn't matter which way you go as far as using an identity. All right, as long as you're consistent all the way through. All right, so that was E. F. So let's say that I have sine of x plus 1 is equal to cosine of x. Now, before I said, like in the previous example, that you didn't really want to deal with equations that had multiple trigonometric functions. You want to try to have them just be one. And in here, we have such a case where we would want to somehow manipulate this. There we go. That's the word I was looking for. We want to be able to manipulate this so that we can replace one or the other. All right. The thing is that as written, we can't really replace sine nor cosine. All right. Now we do have a Pythagorean identity for sine and cosine. All right. Namely that sine squared, well, I'll do it in terms of theta. Sine squared theta plus cosine squared theta is equal to 1. But the problem with trying to solve for sine or cosine here, for example, I'll solve for sine, is that I end up with plus or minus the square root of 1 minus cosine squared. So the fact that I end up with this plus or minus is gonna pretty much make this a little difficult. So what we want to do here is we want to avoid having to use this plus or minus in solving our equation. So rather than try to do anything with that, well, I already know that these work with the squares. So the very first thing I'm going to do here is I'm going to square both sides. So, well, what does that give me? Well, on this side, I end up with sine of x plus 1 times sine of x plus 1. And let's write it that way. And on this side, I end up with just simply cosine squared of x. Now that I have that, well, let's expand the left side. If I FOIL this whole thing out, I end up with sine squared plus 2 sine x plus 1. And we have that equal to cosine squared. Now we can try to use one of these, all right? We can try to use one of those. In fact, we're going to solve for cosine squared here and say that cosine squared of theta is equal to 1 minus sine squared of theta. And replacing this piece right here, we would get that sine squared plus 2 sine x plus 1 is equal to 1 minus sine squared of x. At that point, putting everything on the same side, I end up with 2 sine squared of x plus 2 sine x is equal to 0, right? I added sine squared and I subtracted 1. At that point, I see that on these two, I can factor out a 2 sine x, and I'm left with a sine x plus 1 equals 0. And I'll do this in brackets and stuff. And, well, I've got a product of two things equaling 0, so this first one tells me that sine of x must be equal to 0. The second one tells me that sine of x must be equal to -1. All right? And now that I have that, and by the way, I forgot to say here, in the unit circle, on 0 to 2 pi. But okay, now that I have this, well, I know, well, where is sine of x equal to 0? Well, from the unit circle, that happens at the angle of 0, as well as the angle of pi. Where is sine of x equal to -1? On the unit circle, that happens at 3 pi over 2. All right, so those are our solutions. We've got three solutions, 0 pi and 3 pi over 2. But here's the thing. We need to check that all of these make sense. Why? Because the very first thing we did here was we squared both sides here. All right, so whenever you square both sides of an equation, or anytime you raise it to an even power, both sides of an equation, you have the possibility of extraneous solutions. So let's check it with the original equation. And the original equation, I'll remind you, was sine of x plus 1 is equal to cosine x. So let's check our solutions. And it was sine of x plus 1 is equal to cosine x. So if I let x equal 0, what happens? I end up with sine of 0 plus 1 is equal to cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So 0 plus 1 equals to 1. Yes, it is. So 0 works. Let's check pi. If I plug in pi, I end up with sine of pi plus 1 is equal to cosine of x. This is going to be cosine of pi. Sine of pi is -1, so I have -1 plus 1. And cosine of pi is equal to 0. Is -1 plus 1 equal to 0? Yes, it is. Actually, hold on. I just realized I messed that up. Sine of pi is 0. Cosine of pi is -1. So I had those in the wrong spots. Sine of pi is 0. Cosine of pi is -1. So now I have 0 plus 1 equal to -1. No, it's not. There we go. No, it is not. So this right here is an extraneous solution. All right. And lastly, let's check the last one, 3 pi over 2. and this would yield sine of 3 pi over 2 plus 1 is equal to cosine of 3 pi over 2. Now sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. Negative 1 plus 1 is equal to 0, so that works. So from our original possibilities, only 2 of them are actual solutions, and the other one is an extraneous solution. All right. So again, that might happen anytime you square both sides of an equation. All right, so let's do another one. So that was F. G. Let's say that I had something like 2 sine of 2x minus radical 3 is equal to 0. All right. And this one we're not going to do only on the unit circle. We're going to say just in general. All right. So the very first thing that I want to do here is, or the very first thing that you should notice, is that we have a 2x in there. That's different than before. Before we only had the variable itself. We didn't have anything else with it. So how do we deal with this? Well, what I recommend doing here is do a theta substitution. Let theta be equal to 2x. And then we're going to just rewrite this as 2 sine theta minus radical 3 is equal to 0. So solving for sine theta, well, sine theta would be just simply radical 3 over 2. And the question here is saying, what should theta be so that sine of it is radical 3 over 2? Well, theta would be, let's see, sine is equal to radical 3 over 2 at pi over 3, but also at 2 pi over 3. All right. But the problem here was not about theta. Oh, hold on, before we talk about that, it was in general. It wasn't just in the unit circle. So I need to make sure that I add the period of sine. In general, the period of sine is 2 pi n. All right. Now, the next thing we need to do here is, well, the problem wasn't about theta. It was about 2x. So we're going to say here that 2x is equal to pi over 3 plus 2 pi n, or 2x is equal to 2 pi over 3 plus 2 pi n. And then what we need to do here is divide both sides by 2. So x is equal to pi over 6 plus pi n, or x is equal to pi over 3 plus pi n. Notice I divided both sides by 2 there. All right. So yeah, so in here in general, I would say start by substituting this, and then it becomes a much easier problem, one that you already know how to deal with. All right. Then after that, it's just adding an extra step. All right. Let's do another one like this. So that was G. H. Let's say that I had 2 tan of x over 2 minus 2 is equal to 0. All right. And again, I'm not going to worry about this being only on the unit circle. I want it in general. So the very first thing I'm going to do here is I'm going to do a theta substitution. Let theta be equal to x over 2. So now I can rewrite this equation as 2 tan theta minus 2 is equal to 0. And at that point, I would say, well, that tells us that tan theta is equal to 1, right? Add 2 divided by 2. So from here, well, where does that happen? On the unit circle, it happens at pi over 4, but also at 3 pi over 4. But we weren't only in the unit circle, right? In here, we had no restriction. So what we need to do here is add the period of tangent. And the period of tangent is just pi n. So we add pi n. Now, the next thing we need to do here is, well, the problem wasn't about theta. It was about our x over here. So we're going to say that x over 2 is equal to pi over 4 plus pi n, or x over 2 is equal to 3 pi over 4 plus pi n. Multiply both sides by 2. X is equal to pi over 2 plus 2 pi n, or x is equal to 3 pi over 2 plus 2 pi n. All right. Notice that when I multiply a quarter times 2, they reduce, and I end up with just 4 there. This means with just 2. All right. So again, same exact idea. We start by doing a theta substitution. Make sure you, if we're not working only within the unit circle, make sure you add the period of the function you're working with, and then go back and put it back into the terms of the original variable. All right. So that's h. Let's do another one. Let's do I. Let's say that I had something like 4 cotangent squared of 3x plus 5 cotangent, 5 cotangent of 3x minus 6 is equal to 0. All right. So in here, what we're going to do is we're going to say start by doing a theta substitution. So I'm going to say, well, if theta is equal to 3x, then this equation becomes just simply 4 cotangent square of theta plus 5 cotangent of theta minus 6 is equal to 0. But I don't want to work with all these cotangents, so let's do a u substitution. So let's let u be equal to cotangent of theta. So this gives me just simply 4u squared plus 5u minus 6 is equal to 0. All right. Now that we've got that, this is a much simpler thing to work with than what it was originally. All right, at least visually. So what we can do here is to factor this, start with the AC method. So we have 4 times negative 6 multiply a times t. That gives us negative 24. And we want two values and multiply to negative 24, but add up to positive 5. That will be 8 times negative 3, right? 8 times negative 3 is negative 24, and 8 plus negative 3 is positive 5. So we can rewrite this now as 4u squared plus 8u minus 3u minus 6 is equal to 0. From the first two, we can factor a 4u. We're left with just simply a u plus 2. From the second two, I can factor a negative 3. We're left with simply u plus 2. Since both of those have a u plus 2, we can now factor this as 4u minus 3 times u plus 2 is equal to 0, telling us that u is either equal to 3/4 or u is equal to negative 2. All right. Now that we have that, well, we know the problem wasn't about u. Before it was about u, it was about cotangent. So what we really need to say here is cotangent theta is equal to 3/4, or cotangent theta is equal to negative 2. Now the thing about these is that these are horrible values, all right? In fact, let's look at a possible way to tackle this first problem. We know that cotangent is cosine over sine, and we have that equal to 3/4. So this can be rewritten as cosine theta is equal to 3/4 of sine. But that's not nicely on anywhere in the unit circle, even if I rewrite it as 4 cosine theta is equal to 3 sine theta. All right. So this equation, pretty impossible to solve, at least not using the unit circle, right? Like we wouldn't be able to use the unit circle to solve that. So let's not do that. What we can do here is we can simply say that, well, if I take the inverse of cotangent on both sides, well, I end up with theta being equal to cotangent inverse, or perhaps I'll write it as arc cotangent of 3/4. And then over here, theta would be arc cotangent of negative 2. But we know that because we weren't just in the unit circle, right? The question was not just in the unit circle. We need to add the period. And the period for arc, well, for cotan, right? Because we were working with cotan. The period for cotan is just simply pi n. So we need to add pi n to both of these. But then we know that the problem wasn't about theta. It was about 3x before that, right? So what we can say now is that 3x is equal to arc cotangent of 3/4 plus pi n, or 3x is equal to arc cotangent of -2, and then that plus pi n, yielding that x is equal to arc cotangent of 3/4 over 3 plus pi n over 3, or arc cotangent of -2 over 3 plus pi n over 3. All right. And that would be your two solutions for this problem. And you would leave it as that, all right? You wouldn't, if you really wanted to know what that value is, you would plug that into the calculator, but there's no need to, all right? That could just be simply the last possible solution there. All right, let's do one more, and let's see what we're at. We're at I, so let's do J. Let's say that we had something like 4 cosine squared of x over 3 minus 4 cosine of x over 3 minus 1 is equal to 0. All right. So let's see what we can do here. Well, the very first thing I see here is that I have x over 3's. I don't like that in there. So I'm going to say let theta be equal to x over 3, and this equation becomes 4 cosine square of theta minus 4 cosine of theta minus 1 is equal to 0. At that point, well, I don't want to work with cosine, so I'm going to say let u be equal to cosine theta. So this becomes 4u squared minus 4u minus 1 is equal to 0. Now, let's see if we can factor this. Well, if we do the AC method, take a and c, so 4 times -1. 4 times -1 is equal to -4. And any two factors that multiply to -4 but add up to -4, that doesn't happen, because we have, well, let's look at all the possibilities. We have +1 with -4. That doesn't add up to -4. -1 with +4. That doesn't add up to -4. 2 with -2. That adds up to 0. And -2 with 2 also adds up to 0. So this is not factorable. It's not factorable. However, we know a way around these kinds of things, and it's called the quadratic equation. So I'll remind you that the quadratic equation, in this case, we have it in terms of u. So we're going to say it's u is equal to -b plus or minus square root of b squared minus 4ac all over 2a. So in here, this is going to be u is equal to negative of -4 plus or minus the square root of -4 squared minus 4 times a times c, all of this over 2a. -4 is just +4. -4 squared is 16. -4 times 4 times -1 is a +16. 2 times 4 is 8. So I have that u is equal to all of that. Now in here, let's simplify this a little bit. 16 plus 16 is 32. The thing is that 32 is 16 times 2. And the square root of 16 is 4. So we have 4 plus or minus 4 radical 2 over 8. Yielding, if I divide everything on top and bottom by 4, 1 plus or minus radical 2 over 8 is me over 2. Essentially giving me the possible solutions of 1 plus radical 2 over 2 and 1 minus radical 2 over 2. All right, and that's our values of u. So we've got u is equal to 1 plus radical 2 over 2, or u is equal to 1 minus radical 2, and all of that over 2. But the problem wasn't about u. Before it was about u, it was about cosine. So we gotta go back into terms of cosine theta. So let's see. So what we really have here is that cosine theta is equal to 1 plus radical 2 over 2, or cosine theta is equal to 1 minus radical 2 over 2. And well, those values, again, are not in the unit circle. So what we can do here is simply say that this is just cosine inverse of 1 plus radical 2 over 2. And then cosine inverse of 1 minus radical 2 over 2. But we need to make sure we add the period of cosine. All right, the period of cosine is 2 pi n. All right, so whatever those solutions are, that's what theta is. But the problem was not about theta. It was about x over 3, right? Because we have theta being x over 3. So what we really have here is that x over 3 is equal to cosine inverse of 1 plus radical 2 over 2 plus 2 pi n, or x over 3 is equal to cosine inverse of 1 minus radical 2 over 2 plus 2 pi n. Multiplying both sides by 3, x is equal to 3 cosine inverse of 1 plus radical 2 over 2 plus 6 pi n, or x is equal to 3 cosine inverse of 1 minus radical 2 over 2 plus 6 pi n. All right, and those would be our solutions. All right, and again, it was just a matter of dealing with a whole bunch of substitution. All right, didn't like that we started with x over 3, so replace that. Didn't like that we had a quadratic with trig, so replace that. Once we had this quadratic, we couldn't factor it, so we used the quadratic formula. Keeping in mind that the problem was not about u. Replace back into terms of theta. Use inverse of cosine because this is not in the unit circle, not in any nice way. So use the inverse of cosine to come up with that, as well as adding the period of cosine, and then put things back into terms of x and solve for x. All right. In any case, that is the end of 5.3.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.